I'm Hafiz. I'm a foodie. I love to eat, I love to cook, and especially I love to find the best restaurants everywhere. And on the side, I'm also a recommender systems expert at Agile, but that's not that important. So there is one problem that I have every day, and that is where should I have my lunch at? So here you can see a map of the restaurants around our office here in Hamburg. And as you can see, there are a lot of different restaurants. And of course, some of them I know I've been going to many times and I know what to expect from them, but there are many more that I don't know anything about. So this is one part of the problem. And also, there are new ones opening up every day, and it's really hard to keep up. So every day, I have to choose if I want to go to my favorite restaurant, to the place that I know is the best, or do I want to, I don't know, keep searching, trying some new restaurants in hope that I can find something better than what I already know. And being a data scientist, of course, I want to see what's the scientific approach to solve this problem. So how can I be sure that I'm doing this optimally and I'm choosing the best approach? So the way I see this problem is as a recommender system problem. So we already discussed about choosing a restaurant, but there are other use cases of recommender systems as well. So for example, in any media like Instagram, YouTube, TikTok, there are videos that are getting recommended to users. So recommending them or choosing what video to show is a recommender system problem. Also, this is true for any online shop like Amazon or any other online shop. Or one classic example is casino machines. So if you walk into a casino, there are different machines. You don't know what to expect from them. You don't know the reward that each of them would give. And simply you have to choose which one do you want to play with. So in my opinion, actually, recommender systems are the most important branch in AI. And I'm not saying it just because, I don't know, I work in it, but so right now, when you talk about AI, everybody thinks of LLMs, and this is the hot topic. This is what everybody talks about. But in reality, I would say still most of the public opinion or most impactful decisions are being made by recommender systems. So like social medias are maybe the most influential thing that we have right now. And what content you would see is decided by recommender systems in social media. So I would argue that this is a huge impact, and maybe no other branch can come close to this. And there's also one more use case that I haven't discussed, and that's advertisement. That's also a huge part. And this is also what we do at Agile. More specifically, we are focused on showing ads. Okay, somehow it's not playing. Yeah, anyways, same problem with the internet. We are focused on showing ads between levels, the ads that you see in mobile games. And yeah, I know they are kind of annoying, but that's also what we are trying to do. So what we are trying to do is to make them less annoying or find the ads that would be more suitable to the players. So what they wouldn't get annoyed with and what they would want to install and what they would enjoy. And on the other hand, there's another goal, and that is maximizing the money that we give to the publishers of the game, to the developers of the game, because that's the whole purpose and that's how they can keep building games. So this is two sides of problems that we are trying to solve. And there's a lot of data involved. Hundreds of terabytes of data, billions of ML predictions every day. We are doing, on average, more than 70,000 like 70,000 model inferences per second. And also all of this has to be done in real time. So the scale is huge, and this is the environment when I do my experiments, when I do my tests. So actually, when it comes to choosing a restaurant, I wouldn't make a mistake. So uh, the way I would say the formal representation of recommender systems could be seen as multi-arm bandits. I don't know if you're familiar with them, but anyways, so multi-arm bandits are a setup where some agent has to choose between several options. So one key point is choosing here. There's also the second thing is that you don't know what would happen if you choose one option. So the outcome is not clear for you. And the third point is that you want to maximize some reward. The reward is defined and you just want to maximize it. So for solving these problems, there are multiple approaches, but there is one simple way. You can just estimate the reward that each option would give you based on the historic data that you have, what happened in the past if you choose some option. You just estimate the reward that you would get from each option, and then simply choose the highest, the path that gives you the highest reward. There are many simplifications like assumed here, but this works pretty well to a good extent. So let's move forward with this approach. But then there is one problem here. What if you don't have any data? So you can estimate based on previous data for the options that you already have tried, you have some data, but if there is no data, how can you estimate this new option? And I don't know if you've heard the cold start problem, but this is what it's referring to. So if you don't have any data, how would you estimate the outcome for some option? So how do you think we should solve this problem? Any ideas? And please shout because I can't see anything. The light is too bright. Red peel? Okay, yeah. It actually, yeah, makes sense that there is no escape from choosing new options. And if we just stay with what we already know, we're going to lose relevancy. We're not going to find any new things. And basically, we're going to stuck wherever we are. So we just have to try the new options, and there is no way out of it. But then after deciding that we have to try, then the follow-up questions come along. Like, how many times do I want to try one option? How many tries would I give? How many chances would I give, for example, a new restaurant? Or each time that we are choosing something new, there is a cost to that. So uh, for restaurants, it would be there is a price that you are paying for the food that you are going to. And then if you're not satisfied, there's also an opportunity lost. You could have gone to the restaurant that you like the most and had some satisfying meal, but you didn't do that. You ended up with something that was not optimal. So this is also a cost. And how can you minimize this cost? And then also, not all of the tries are equal. So let's say, for example, for one restaurant, there's this new restaurant. You try it every day for a week, and then every day you order the same thing. So all of them also on lunch, for example. So you can, for example, get this information that this restaurant doesn't have this, like this option on this restaurant is not that good. But what if you tried another option on the menu? What if the other option was good and it could have been your favorite meal for the rest of, I don't know, your life? You can't just miss on opportunities like that, and all of the trials are not equal. Or what if you, instead of lunch, went for dinner there, and on dinner time they have a different chef that is perfect, that is really good, and you simply wouldn't know if you just try it in the first setup. So even if you want to try it, it's important where or in what situation do you try this new option. So these are the problems that come along. So let's move forward a little bit. So if we go back to estimating the rewards for everything, we have some estimations of our different options. So here we have three different options for simplification. There is a good option that you know, there is a bad option that you already know, and then there's a new option. And I would argue that if you had to estimate without any information, what you would do is just estimate the average. Uh, if you have no data, then your estimation is going to be exactly the average. And my argument for this is that if someone asks you, like, what's the best restaurant in this situation, you would go of course, the good one. But if you move the good one out of the picture, uh, what you're going to guess is like if someone asks you for a recommendation, you're not going to recommend the bad one. The bad one, you already know it's bad, so you're just going to go with the new one. So my argument is that if you have no data, if you want to estimate, you're just going to estimate the average. But that is not completely, or that is not the whole picture. This also depends on how risky you want to be, or there is a risk factor involved in the situation. So even though there is some restaurant that you know it's good, there are some times that you would give a new option a try. Uh, and the reason is that it's not actually one single point, but what you have in mind is actually a range. So basically, for the good one, you have a pretty narrow range. You are confident that it is going to give you a high satisfaction. And by the way, from this point on, we are modeling it from satisfaction from 0 to 1. And then, okay, for the good restaurant, we have a like we are pretty confident that the satisfaction is going to be somewhere around 0.8 to 1. And for the bad one, we already know what the range is going to be. And for the red one, you can see that since we have no data, even though the estimation, if we had to guess one number, would be the average, but it's actually a wide range and it's everywhere. It can be everywhere because we have no information about it. Actually, if we wanted to be a bit more accurate, what we have in mind is a probability distribution. It's not just concrete ranges, uh, but yeah, a probability distribution where it peaks near the averages. And then we can see here, for example, for the red option, it spans everywhere because we have no data over it. And the probability distribution that I'm using here is beta distribution since it's bounded between 0 and 1, just uh, for clarification. So what if we change our approach and when we want to choose one option, one outcome, instead of estimating the average for everything and then taking the maximum, what if we choose one sample from these probability distributions? So we have these in mind, and I would argue that this is what we also do in reality. So we have these in mind, and we take samples from them. So when we are taking random samples, for the red one, the sample can end up anywhere. And this situation is possible to happen that, okay, if the green one is unlucky, which the random sample that we are taking from its distribution say somewhere more close to 0.6, and then the red one is lucky. This is what can happen, and in this situation, what we would pick is the new option instead of picking the known option, which is the known good option, which is the green one. And I would argue that this is also what we naturally do. So even though there might be some good restaurant that we know every day, there comes one day, or like it just happens that you don't feel like it. And then there is multiple restaurants that you don't know, but suddenly you have a good feeling about one of them. You just want to give this one a try. So this is more in support of this is also how our brains work. That we have this distribution in our heads subconsciously, and every time we want to make a decision, we actually just draw one sample from it. So this way, what would happen is that if we just do this, there is some chance for the new options to be picked. And this chance is related to what we know from others. So basically here, we're not going to pick the red one all the time, but I would say somewhere around 10% of the time, because like the good one has to be unlucky and the also unknown one has to be super lucky so that it would be picked. So we just distribute the new trials evenly everywhere. And there is one more point. When we get some data, when we try it out, and when we get some outcome, then we update our distribution. So what can happen is that naturally, super smooth, we would update our distribution, and the more data that we have, the more confident we are in our results, and the distributions would get narrower, and the chance of picking something suboptimal reduces. So slowly we converge to a place where we would always pick something optimal, but it's never 100%. The chance just reduces. So this approach is called Thompson sampling. Uh, Basically, yeah, here we, instead of taking the average estimate, we take a random sample from the probability distribution model of each option. And then after we did this, the rest is the same. We just pick the highest. We just want to maximize the reward, so we're just greedy. And this is also mathematically proven that this is the optimal balance between exploration and exploitation. So if we want to get the best results in long run, this is the way that we should do it. So everything sounds super good until this point. We have a way that mathematically is super sound and is good, but then it comes the implementation part. And it's not as easy. So when we want to do the implementation, especially I'm going to focus more on how we did it at Agile. So here it's a schematic of the model that we use. So we have this model, this fancy neural network model, which you can see the high level here. And especially if you are interested in knowing this in more details, there was a talk that I did last year at Bit Summit about deep and cross layers. I'm going to add the link or QR code at the end. If you're interested, you can look that up, but I'm not going to go into details here. But we have a fancy neural network that gets the features from each situation and predicts the probability or the average outcome satisfaction that we would get, or for example, the satisfaction of each user from seeing each ad. So what would happen if we just take this model and put new options into it? Same thing that we discussed. So the new option would be predicted average, and the average is never the best. So if we are taking the best option always, we would never choose this option. And when we would never choose it, then we would never know if it's good actually or not. Same problem that we had before. So one solution that we can have here is to, instead of just predicting the average as we usually do, so if you see the top parts here, this is the network that we previously had. We can add another head to the model. And this new head, instead of predicting the average, is going to predict the variance. This one is going to predict or give us how sure the model is in its own prediction. So basically, having these two parameters, if we have the variance and we have the average, we can plot the whole distribution. We would know the exact distribution, and then after we have the distribution, we can draw one sample from it. So once we have these two for every option, we can take our samples and then follow the rest. Just pick the highest one. This one sounds good, but there are a few problems. One of them is that training a model to predict its own uncertainty is not as straightforward. You need some custom loss functions. There is something that is not so mainstream, and it's not going to be easy. Another thing is that you need to retrain your model. You might have a good model that you already tested and you know it's really good, but if you want to do this, you have to retrain the model. And then also you have to change the model architecture because you need another new head, and adding this new head can have effects everywhere. Your model might not converge as good anymore, and then also validating the accuracy or calibration of this uncertainty. So if the model is predicting its own uncertainty correctly or not, these are all the questions that are not easy to handle. But what if I told you there is a simpler way? So let's dive a bit deeper into the architecture. So uh, the first embedding layer and the cross layer are okay. Let's go a bit deeper into the feed-forward layer, which is the usual constructing part of almost any neural network. Basically, no matter the architecture, no matter the task, even uh, I would say the language models, all of them have these dense layers usually at the end. What if we zoom a bit more into this, and specifically on the last layer? So there is a bunch of neurons, depending on the hyperparameters of the model, and all of this together form this final output that you have. And this one is not it's a linear combination of them, but for simplicity, let's say it's just an average. So on the last layer, we don't have any weights or biases. So the final output, let's assume, is just the average of the last layer's nodes. Uh, so here, if you see this picture, what would you assume? So what we can do actually is to look each of these neurons, last layer neurons. Let's assume they are one of our, I don't know, one separate judge or critique that is going to uh, basically estimate the final value. Or like, let's say these are each of them one of the friends that we asked about a specific restaurant. So if you see all of your friends or all of the critics are giving a good score about something, I would argue that this means that there is a good chance, or we are certain that this is a good option. There is not much uncertainty about this option if everybody agrees about this. So, and the way I argue that these are similar to judges is that basically these high-level neurons that we have, each of them has access to all of the high-level features of the previous layers, and each of them form an overall opinion about the whole thing. So we can see them each one as a separate critique, and each of them is trying to capture some high-level information about the final result. So basically, if we see this picture, what we can assume is that the model is pretty sure about the results. If it says it's good, then there is not much chance or not much uncertainty into it. And there is two things. So according to the data, we know that there is not much uncertainty if a model predicts this and the model is trained well. And also, it's not just good for valid for good options. The model can also say, like, all of the neurons can say it's bad, and if all of them agree that this is bad, then we can assume that this is bad. Or even it can be average. Like, for example, average in restaurants for me is a doner place. It's never, I don't know, it's never amazing, it's never life-changing, but also it's never disappointing. So this is an option that is average for me personally, but there is a high certainty about it being average. But this is completely different than an option which has high uncertainty. And some people, something like this, that some people would say it's super good and some of them would say super bad. So basically, if we see this picture, I would argue that we need to pay more attention. We don't have enough data. We're not sure about the results of this thing, and we need to explore this part a bit more. So if we want to do that, there could be one simple solution. Instead of if we take into account all of these neurons, the result that we get is something average. The output of the model is average, but also for the option that we are sure that it's average is going to be also average. So what if instead of taking every neuron into account, what if we just do it with a subset? We just randomly select some of the neurons, and if there is high uncertainty, what can happen is that this random subset that we are taking could be some that are super good. So even though previously this option was predicted average, then suddenly it can be predicted as a good option. And then also if we randomly select the bad ones, it's going to be predicting bad. But if the option, everybody is agreeing about this, all of the neurons are predicting the same, uh, no matter what subset we choose, all of them are going to be on the average. So basically, if we do this, if we just randomly select the subsets, according to the model's uncertainty, the variance of the outputs can be increased. So the places where the model is not that certain, we have a high variance of the outputs. And the places that we are certain, then it's going to be always average. Uh, and I think it sounds familiar, selecting a subset of neurons and only using them. This is what we know as dropout. So dropout is known, but mostly in training. So when we want to train and we don't want the model to overfit, this is a well-known technique to just add some dropout layers between each of our layers to help the model train better and everything. But this time we are adding it during inference time, not just the training. So even in production, even when we want to get the final results, we still keep the dropouts active. And this is what we call Monte Carlo dropouts. And also, one more point. This is not just the intuition that I explained to you. So here we saw that taking random subsets of the neurons would do the two steps together, just predicting the probability distribution and then taking a sample from it. Just by selecting a subset, we just took some sample of the distribution. And the fact that just using this dropout in production is completely equivalent to predicting a distribution and then drawing a sample from it. There is mathematical proof for that in the paper that I'm also gonna add the QR code at the end. So if you're interested, you can read it. And one more point is results. So this part is a bit tricky. If you want to evaluate such a thing, if you have some strategy for exploring new options, the problem here is that imagine I'm the one who always explores the new option, and there is one other friend that just asks me everything. So in general, I'm going to have a worse experience. I'm just trying all the options, and more often I would find out what's bad and just tell it to him, and then he wouldn't just go there, and he would always have the best experience, but also know if there is something new happening. So if we want to run an A/B test for such a scenario, and we use every data that we have, this is the situation that is going to happen. If we have two models, that one of them does the exploration, the other one always is greedy and is picking the best option, but both of these models are trained on the same data, on all of the data that we have, then the greedy model is always going to be showing better results. But this is not true. The better results that we are seeing on the greedy one is because of the exploration and the data that the other one gathered. So if we want to truly have a correct A/B test, we have to separate everything. We have to separate our data pipelines, our training pipelines. Everything should be separated in two. And also, the exploration is not going to pay off immediately. We have to try some new options, and then after we have some information about them, then we can train better models, and those better models are going to give us better results. So if we want to truly A/B test this, we need to separate our whole system into two, everything, and then run it for a long time to see the results. And for us, that was not really possible, or I would say desirable. So we just deployed it in production. But we can see some high-level results. So there's this dotted line here, which is where we deployed the model. And the whole plot is a plot of one of the engagement metrics. So let's assume it's the amount of interest of users in the ads that they see. And we can see that before it was kind of stable, and immediately after deploying it, we see a drop, which is expected because we are exploring new options. We are testing some things that we didn't know. But after that, you see a constant upward trends to the levels that we never had before. So although it's really hard to associate these changes with the like these results with the changes that we did, but it matches the timeline. But also, other than that, there are some obvious points that, okay, after deploying this, we didn't have to worry about new options anymore. They are just smoothly being added to our systems, and it's not suddenly we just add a new option, we show it thousands of times, and then this disrupts our system, and then we have to make a decision if this is a good or not. So basically tuning the numbers, how many times or across what dimensions do we want to show this new ad. None of these we had to take care about anymore. And also, previously we had to uh, like add some clear boundaries if some option is new or not. If it's new, then we want to give it some chances, and then at some point we should have decided that it's not new anymore. We have enough data and we should treat it like others. But here with this option, we don't have to have clear boundaries, and all the options, they would still gather some data and they still have some chances of being chosen even if they are showing bad results. And the chances of them being picked is completely related to the basically results that they have shown. But we would never stop gathering data. So I would argue that these points alone is worth it to add it regardless of the results. So the amount of stability in the system that it adds, continuous data gathering, and also the reduced headache of tuning the numbers is alone enough to do this. Thank you for listening. These are the QR codes for the things that I promised. And if you have any questions, let me know.